Hey Quad folks, today I will try to explain a little bit about the history and the development of the 2-inch Quadruplex Headdrum and give you just a general overview of some of the things that went into the development of the Headdrum and the tips and the materials that were used in the early years running up to well, what you would call the modern day, 1972 being modern. So to begin, we will need to take a look at the mechanical design and development, and also the materials that were used during the various stages of the development, to get a little better understanding of how things were interacted, during each stage or each period of time. 1914, permalloy was invented by a fellow named Gustav Elman at Bell Laboratories. Then the next development was around 1936 with Sindust by a fellow named Hakara Matsumoto in Sendai, Japan. So you get the connection there, Sindust, Sendai, Japan. The next development was 1939, alphenol, and by Matsumoto again and associate Hideo Seato. I hope I'm saying that right. And then later on, in the 1950s, we have the Alpha Seal alloy, which was available in Japan in the 1950s and became available here in the U.S. in the 60s. And so what these have in common, these alloys, basically was the iron. Every one of them contains iron. So you see we have 20% iron, Fe, permalloy, Sindust 85%, alphenol 84%, and Alpha Seal 85%. What distinguishes these alloys is the percentage of the metals that are mixed with them to give them their unique properties, and also the process in which they are combined or formed is somewhat different from one to the other. For example, permalloy is 80% nickel. Sindust is 9% silicone and 6% aluminum mixed up with the 85% iron. Sindust is just that. It is a powder metal, powder metallurgy that is ball milled into fine powders, like the consistency of baking flour, you know, that fine powder. And the way they did that is they have a rotating vat, and they would actually put balls, steel balls, or ceramic balls in, and they would roll around in there and just pulverize the material into a fine powder, ball milling, ball milled, powdered metallurgy. So this is all powder metallurgy. This material is mixed, and the three combined, and then it is sintered in a sintering process. That's sinter with an S, sintering, and that's, you know, compressed under a high heat into a solid form. And which, by the way, that is the way most ferrites are made today, you know, sintered, powdered and sintered. Alphenol came out of the sindust process in 1939, and we have a little less iron, 84% iron, and 16% aluminum. That's aluminum, Al, iron, Fe, alphenol. Alphenol was a ductile process. What's ductile? Ductile is like how you make steel in a steel mill, a roller mill. You heat it up to a liquid form in a crucible, and you pour it out and you roll it in a sheet, and you roll it between rollers, and you can you know, get the desired thickness that you want by moving the rollers closer together, etc. and so forth. And so you pour it out and you roll it just like you would in a steel mill process. That's ductile. It's a ductile metal process, and that's alphenol. Then later on, around 1950, alpha seal, which is, you know, sindust, alphenol, alpha seal, again the same. So we have 5% aluminum, 85% iron, 10% silicone. Aluminum, Al, iron, Fe, silicone, SiL, Alpha seal. This is a cast ingot form, and that's, you know, you heat it up in a crucible and you pour it into a mold, a cast ingot. And this became available in the 1960s in the U.S. and Hamilton Watch Company, they were maybe one of, or maybe the, they had one of the most advanced metallurgy departments in the world at that time, and their focus, you know, was making watches. And of course, metals is the main ingredient of a watch. So they were all about metals and how to use them and what kind of alloys makes the better watch components. And they got interested in alpha seal as maybe a metal that could be used to make a watch spring with. And it's at this point is when the Ampex Corporation, the video guys, got interested in alpha seal as a possible metal for making tips for the video heads. Now there has been, you know, throughout the development of the video head, all these materials have been used at one time or the other. But the durability of the material is what Ampex was trying to advance. You know, the durability as in hours of use, head hours. Permalloy having the least or the lowest, very soft metal compared to some of the other metals. Sandust probably was the next one, which was a lot harder than permalloy. Alphenol was somewhat softer and was more akin to permalloy as far as the durability. It had a very high rate of wear, you know, so you could get maybe 100 good hours out of alphenol. So very few video heads were ever made using alphenol early on, you know, in the 1950s, the late 50s. And then of course after the alpha seal became available in the 60s, then we saw alpha seal from then on became the predominant material of choice because of its has a very low wear rate. You know, you get a lot of hours, you know, 300-400 hours on an alpha seal head, whereas you could only get maybe 100 on alphenol, and then even less on permalloy. Permalloy has found its use mainly in longitudinal heads, you know, such as audio heads and things like that. And permalloy in that form would be, you would have rolls of permalloy. This is about 1 mil thick. And if you were making an audio head, what you would do is you would stamp pieces out of this strip of metal into your pole pieces for your audio head, and you would just laminate them one on top of the other and stack them up and build up a thickness of these laminations to the thickness or the track width that you needed, you know, to make the head. And so, you know, permalloy in various different forms and under various different manufacturing names found its use mainly for fixed heads, longitudinal heads, audio type heads, you know, because of its ability, you know, to be stamped and laminated. Video heads. This is an early form. I don't have an example here. This is a photograph from my friend Bev Gooch, his collection. This is a photograph of his permalloy quad head. It was an experimental prototype, and as you can see, the 4 permalloy heads mounted to a crude drum, and the heads themselves, the tips, are more of, you know, a laminated or an audio type head, you know, in the way they're constructed and mounted on a drum. This example is in the Tennessee State Museum now. That's one early example. This is an example of a permalloy quad video head. Let's see, dump one of them out here. Can you zoom in on that? Get a good. Now this is the aluminum block here. It's 2 pieces of aluminum. And see, there's a little screw in each, 2 screws there. And then of course the other side has been drilled and tapped. So the 2 blocks of aluminum have been screwed together. And then to this, you have the 2 pieces of permalloy that have been epoxied there, and of course the gap has been formed. Now to this would be known as what a composite video head, and this is one of the early developmental heads. Fred Post at Ampex was responsible for. To this you would add a ferrite ring with the coil wound around the ferrite ring, and that would be affixed to this. The next example would be a composite head. Which you have, or a sandwich head, and so you have, you know, the 2 pieces, and there's not a whole lot you can see here. I don't have one that, you know, I can take apart and show you, but it's 2 pieces of brass that have been screwed together, and then below that the actual tip and the ferrite block have been epoxied, and then the wires. Can you zoom in on those wires? Can you see those?
Let's see.
The 2 little tiny wires come out, and they solder onto the little posts here. And that's your head coil wires. This is a solid drum. The transducers are epoxied into the drum. So once you align it and glue it, you're done. There ain't no adjustments here. Other than, if you notice these little holes here around the outer rim, those are balancing holes for balancing slugs, and see, there's a slug there. And you could, you know, put one in either side or one in one side as needed to get a roughly a crude balance, you know, of the drum, so it'll spin without a lot of vibrations. These types of heads early on you know, in the late 50s, before time-based correction. When you made a recording with these heads that needed to be played somewhere else, you sent the head with the tape. So this is that era, you know, when you had to play a recording, you had to send the head with the tape to you know, preserve the geometry, because these were non-adjustable, and you know, they're glued together and you can't move anything, it's set. And the thing that came into question when making the drums was how to make them all the same, you know, as far as the alignment. And of course you couldn't get that good doing this, you know. It came out the way it came out, and there it is. And practical meaning that it worked and it didn't fly apart. But you had to send the head with the tape whenever it needed to be played somewhere else. That's good, but it wasn't really, you know, where it needed to be. But that's another step in the development. Then a little more advanced drum was developed at Ampex, and this is a brass drum, and the dime transducer. Only now we have a little adjustment apparatus here. No balancing adjustments, and we have two holes here to mount this drum to the motor. This was an experimental prototype in the development. This eventually turned in to this, the alphanol tip. Take the tips out here for just a minute. So now we go from this, and now you see there's some adjustments have been added by slots being cut into the drum. Mounting holes, 4 now. And into these outer holes, which are threaded, you could screw in a tapered screw, an Allen type tapered screw. And that allowed you to forcibly, you know, move each quadrant a slight amount to give you a little bit of adjustment to set the quadrature. So that was a step forward, but here you're bending metal. You know, so metal only wants to bend so much, and then it may or may not come back to where it was previously. So it's better than this, and a lot better than this, but still we have some issues there, you know, it's not perfect. And so this is still a brass drum, and it's plated now on the rim. It's brass plated with chromium. So this would be a finished design here. You know, if you're looking there. And so this is the finished built-up drum. And these are composite transducers. What I mean by composite? Well, let's see. We can find us a picture here. This is an early composite using a ferrite core and metal on the facing edges. And this is a gap, the alphenol hole tips, and then you'd have a ring of ferrite, and then the coil around the. And this would be this. Be that right there. And of course, our example doesn't have the ring on it, so we're looking at the alphenol tip. And then you get to this later composite, which is you have an alpha seal head core and a ferrite block with the winding coil. That is this type of a transducer would be this design, and that's this. By the way, I'm taking this from an Ampex book. This is something that Ampex had in the mid-1980s. It's just kind of an overview of a very general, overview of their, their video tape products and processes and some of their history of how they did things at Ampex and developed all this. Now this book is probably not that common. I don't know if you'd ever find one of these or not, but for those of you that are interested in this information, this is Television Engineering Handbook by K. Blair Benson. This came out in 1986, and much of the information contained in the original Ampex textbook is included in this book, which this was put out by McGraw-Hill, and there's a lot of these books around. You can find these fairly easily and cheaply. And this is the 1985. I think I said 86. So this is a fairly common book that you can find, you know, in the secondhand stores and eBay and whatnot. Now, what we were talking about, videotape recording, we go here to 15.1. You'll find the same information contained in the original Ampex book. And it really goes fairly deep. I mean, if you really want to learn what's going on, the theory, you know, and the development, you can find the answer here, or many of them. Let's see, here we have our drawing that we were just looking at. So it's duplicated in this book. And so for those of you that would like to, you know, to study deeper, then I would recommend looking around and finding one of these 1985 issue handbooks by Benson. Okay, moving on, we get up to the Mark X era. And Mark X is when things really became workable, you know, and this is the Mark X drum assembly, and this is the Mark IV. So we were here and we went here, and the fellow that had a lot to do with the mechanical changes and the design implementation found in the Mark X at Ampex, his name was John King. He had a lot to do with, you know, the development of that design, the mechanical aspects of it. And so now we're leaving behind the slotted drum quadrature. Now we have springs. You have a beam spring, and it's pushing against the tip, and so from one side you have the beam spring pushing this direction, and from the other side we have our tapered screw. It's not in the actual drum now, but now it's in a relief slot on the back side of the spring block. And as you screw this in, it's tapered, it pushes it over toward the left more and more and more. So you can easily line up the quadrature now between the four heads. you know, with just an adjustment. And also added to the Mark 10 is we have an eccentric pin in a slot and a hole back here that allows you to set the radial alignment from the center out. So once you get the 90-degree quadrature set, then you can come back here and you can line up your gap from top to bottom along that radial or that radian line. So as your tips wear down, they're in alignment all the way down, you know, from new to wore out, and you don't see much of a skew as your tips wear down, you know, because you're wearing down in alignment. And so that's the Mark 10. This is an original Mark 10. As you can see, that the shoes are not anodized. So Ampex, they would anodize these shoes black. And I think later on Spin Physics, when they started rebuilding in the 70s, they would anodize their shoes blue color. And so this is one of the early Heads, unanodized aluminum shoes. And again, all of these came from my friend Bev Gooch, part of his collection, and he was kind enough to bestow these on me for study and you know, the work that I do here, which I studied with Bev about 5 years on head rebuilding and tip fabricating, and I learned a lot from Bev, and I don't think there's any way you can ever learn everything a person like Bev knows, but I took a lot of notes, made a lot of videos, and committed it to memory as good as I can, you know, and I share it here now with anyone else that wants to know. And this is just, you know, a primer. If you want to learn, you need to, you know, this will get you going in the right direction, and you can learn on your own now that you have a little bit of a seed knowledge about all this stuff. And that's kind of what I hope you do, or maybe what will happen is somebody will see something here that may make them want to know a little bit more and learn a little bit more about this, what's becoming a lost bit of technology nowadays. Anyway, moving on. So now we have a head developed in the 1960s, the Mark 10. Which incidentally, the Mark 10 drum design this is the same drum that's used on a Mark 15 or a Mark 20. It's the same identical drum, same thing. Now, there are differences, you know, in the assembly itself, a lot of differences, but the basic drum design is the same in a 10, a 15, and a 20. Now there is one distinction to be made there. The ball bearing that did not have the rotary transformer, you know, had a slip ring there, and the air bearing with the rotary transformer, it just had the motor shaft sticking through that went into the rotary transformer, like this. This is an air bearing. So, you know, all you got there is just the end of the shaft. So there is a little difference there in the motor shaft. This is an alpha seal tip core. Can you see that with your camera, or should I take it out of the little bag? Maybe you
take it out.
Might have a little bit of a glare, I guess, with that bag. Well, drop it. Let's see. Let's put it in this little box here. Maybe it'll show up a little better. There now. That's tip core. That was made at Ampex. And so that's a new one. Well, new as in 50 years old. Maybe unused would be a better word. Uh-oh. Oh, there we go. You can sort of get an idea what an Ampex core looks like. And then of course it is epoxied to an aluminum shoe. Let's see if I got one. There's one. And there's the alpha seal tip core that's been epoxied to a shoe, aluminum shoe, and the alpha seal core. So you glue this to this, and then you take this piece and you bolt it on to the drum. Now, I know that's a very small, tiny thing, and here I've made a little model to maybe further illustrate a little better what that is, the actual tip. So here we have two pole pieces. One pole is just a, well, let me back up here. If we were actually making tips, this would be bonding blocks, I should say. So we have a rectangular block, and this would be about 3/10 of an inch square and about a 1/2 inch long. And same here, same dimension. Into this block we would grind a channel, just a little, a little U channel, and then here we would have a channel ground on a 45-degree angle to this plane here. So this would be 0 and that would be 45. And kind of like a V looking notch. And So we take the two bonding blocks, and if we're using the early method of capillary bonding with glass rods, then we would need to separate these with some shims of about 50 micro inches thickness. So then we would have our shims here and here. And then we clamp it together with our clamps, which, you know, in reality it's not a rubber band, it's a metal clamping jig, but you get the idea. We clamp all these pieces together with a clamping jig, so we have our two pole pieces separated by our shims and clamped together. And then into the winding window in the back gap, we would insert our glass rods, our brazing rods, and we would then put this in a vacuum furnace and bring it up to a temperature where the glass flows, and through capillary action it'll be sucked back into these gaps, these little voids, gaps between the two pieces. And so that forms a glass gap and joins these two pieces together. Bonds, I should say, glass bonding. Well, okay. Everything went well, and you take it out of the oven. And now you have a bonded block. And from this, we would slice our tip cores. So this would be our tip core with our two halves and then the glass bonded gap. And so from this one block, we would slice several tip cores from this one block. And now, depending on what you're slicing, the material, well, modern day it would be ferrite, manganese zinc. That's a very hard and brittle material. You'd have to use a diamond saw if you were sawing manganese zinc. You know, it has to be cut. It can't be worn down like, you know, you would wear through with other methods. You have to actually cut ferrite, and the only thing that'll cut it is a diamond. So you would allow, you know, for the thickness of the saw blade, or the cutter blade, and cutting this, you would cut these, if you were making 10 mil tips, then you'd allow the width of the saw blade that distance, and you would want to cut these at about 12 mils or 12 thousandths. So you would get your rough tip out, and it would be around 12 thousandths. And from that, you would lap it down with a lapping machine or by hand, or, you know, diamond lap it down, and take about 1,000th off of each side to lap it down from 12 to 10 thousandths thickness. And that accomplishes two things. That gets you down to the thickness you need, the track thickness of 10 mils. And it also polishes these sides, you know, to a mirror finish. And so you wind up, after you do all that, with a tip. Well, I hope that this little feeble explanation of mine may enlighten somebody as to where some of this stuff came from and what it is, and you know, maybe the evolution, you know, which part came first, and how it all evolved over about a 25-year period, you know, from the mid-50s to the late 70s, and, you know, in the development of the quad head and the tips and the materials that went into it. And, you know, as if you start looking online or asking around or wherever you go, it just seems like you cannot find much information about any of this. I was lucky and I had a friend that worked at Ampex and, you know, could tell me all about it, and that helped a lot, believe me. When you think of, well, there weren't that many people anyway, you know. I think at Ampex, Fred Post was maybe the guy, and then you had Alex Maxey, which had a hand in the heads. Maybe a lot more into the helical development than the quad, but he certainly had a hand in the head department. And then you had people like John King at Ampex, which was more of a mechanical person, you know, that developed a lot of the mechanical aspects later on. And then my friend Bev, who spent his whole career there in the head development department at Ampex, he knew all these people and, you know, had seen a lot of this stuff. And so that really boosted me, you know, just being able to have a go-to guy, you know, that I could talk to and ask questions, and that could actually show me, you know, with real examples, you know, and, you know, make it real. And so I hope I've at least done that, or conveyed a little bit of that to you. And I encourage you to study more. You know, if you're interested in this, don't take my word for any of it. Anything I say, you can go out and prove it yourself, you know, through patents, patent office research, or some of these books like the television engineering book, which a lot of that information came right out of the Ampex publication, which was, you know, a product of all these people's work over about a 40-year period. So I guess my capacity is maybe as a presenter and just someone that can make you aware, or a little more aware of some of this stuff, and maybe point you in that direction, you know, where to look if you want to study for yourself. And if I can do that, I think I've succeeded. It's help you out a little bit on some of this head stuff.